Welcome to our presentation on the redesign of the Neudeflat Utrecht. The Neudeflat is situated in the center of Utrecht. Built in the 1950s, as a start of the modernistic rethinking of cities, it's the only plan realized from that era. Due to this fact, it's the only high-rise in the historic center, which offers great view over the city. The structure consists of a structural core containing the stairs and elevators. The surrounding concrete floor slab is supported by a network of beams and columns. The facade consists of glass window strips with aluminium framing. At the backside, an additional structure houses the emergency staircase. Because the Neudeflat was built in the 1950s, it does not live up to current climate standards. We will now look into several problems that occur in the current state and are brought forward by user experiences. One of the problems is that none of the structural elements, like the aluminium framing or concrete structure, are insulated. This forms a thermal bridge, causing heat loss and condensation. On the office floors, the offices are situated along the facade, forming a common space in the center. This space has poor daylight penetration, which makes it a dark and uncomfortable space. Individual temperature control is very hard, causing one office to be too hot and the other too cold. Occupants have to open their doors to stabilize the temperature. The aluminium frames date from the 1950s. Due to their age, cracks have formed in the openable windows, causing a heavy draft. The Neudeflat has no ventilation system. On hot days, this easily causes overheating, leaving the openable windows as the only means of cooling. On the top floor, the facade is set back 1.5 meters, forming a balcony. The possibility of going outdoors is very much appreciated by the occupants and offers a great view over the city. We will now look into our interpretation of Ben Bronsma's earth, wind and fire system. At the intake shaft, a pressure difference draws in the fresh air. Here, a cascade makes the air accelerate, causing a high pressure at the bottom. At the same time, the water, with a constant temperature of 13 degrees, heats up or cools down fresh air, humidifying or dehumidifying it in the process. At the bottom, the air is heated up to room temperature. Then the air is distributed through the atrium. Small vents at the floor level draw the fresh air into the offices. The air then heats up and rises to the highest point in the curved ceiling. Here, the air is recirculated by the integrated climate ceiling or exhausted to the solar chimneys. In the solar chimneys, the air is heated up, causing it to rise and leave a low pressure at the bottom. Higher up, the heat exchanger captures the surplus energy and stores it for later use. At the top, a vertical windmill assists in the extraction of the exhaust air, generating power in the process. will now elaborate on our design interventions on the Neudeflat. An atrium will be made in between the central columns. The climate cascade will be placed at the center of this atrium to minimize external influence. At the south, east and west side of the building, 3 solar chimneys will provide the offices with continuous ventilation. The atrium does not only make room for the climate cascade, but also brings in light into the dark center. Air moves up through the atrium to the offices, providing them with fresh, climatized air. The building will be provided with a new facade, eliminating the earlier stated problems. The curved ceiling guides the hottest air to the exhaust valve. From there, the air is transported through the central core to the bottom of the solar chimney, maximizing its effect. At the top, the vertical windmills assist in the extraction on cooler days when the solar chimney doesn't provide enough extraction. This concludes our presentation of our design interventions on the Neudeflat. We thank you for watching.